Now, we already know what primary keys are. These are single attribute or a combination of attributes that uniquely identifies each entity instance. And having a primary key in your entity guarantees that we have entity integrity. And it works with foreign keys to implement the relationships. Now, how do we select the primary keys? We have what we call natural key or natural identifier. These are real-world identifiers used to uniquely identify real-world objects. They are familiar to end users and forms part of their day-to-day business vocabulary. And usually, they are being used as the primary key of the entity being modeled. Now, in selecting a primary key, make sure that we are following these guidelines. First, they are non-intelligent. You don't need to think a lot about your primary key, chosen primary key. It should not change over time. Preferably just single attribute because having composite primary keys can be burdensome. And preferably it is numeric so that you can apply some manipulations on your primary key. And of course, should be security compliant. You did not want to select a primary key that is easily distinguishable or easily hackable by other people. So in the previous slide, we have seen that ideally we need to have a single value primary key. But when do we use composite primary keys? We use composite primary keys if they are identifiers of composite entities, and each primary key combination is allowed once in the many-to-many relationship. And if they are identifiers of weak entities, meaning we have strong identifying relationship with the parent entity, and it represents a real-world object that is existence dependent on another real-world object. And this one is represented in the data model as two separate entities in a strong identifying relationship. Here we have an example of usage of composite primary keys, which is a breakdown of our many-to-many relationships. If you can recall, the class and student has a many-to-many relationship, and we created a composite entity or a bridge entity between them called enroll. And the primary key that we're using for that new entity are exactly the primary keys that we are using for the class and student entities. So far we have talked about the guidelines on choosing our primary key. That what happens when there is no natural key that you can choose as your primary key, or if your candidate key has embedded semantic contents or is too long. Then that's when we make use of surrogate primary keys. Using surrogate primary keys require ensuring that the candidate key of an entity in question performs properly. And in here, we're going to make use of the unique index and not null constraints. Now, let's take a look at an example to show us why do we need to use surrogate primary keys at times. In this example, we have a table that captures the reservation of a certain hotel for their function rooms. Now, if I'm going to ask you what will be your chosen primary key, what will be your answer? So let's take a look at each of the possible attributes that you might choose. So you might be choosing date. Of course, this is not a good primary key because you have multiple dates, and as we all know, primary key should be unique. So let's take a look at the combination. How about the combination of the date and time start? Again, there are some instances in your records that has the same date and time start. So probably you might want to add, okay, let's add time end. And it's still the same. You still have the same combination. So it still doesn't give you a unique identifier of your record. So you might be asking, okay, let's add the room. So your first instance of a possible primary key is the combination of the date, time start, time end, and room. But if you're going to choose that as your primary key, it's going to be hard for you to navigate through the data or to get to the data that you would like to achieve. And so if we have, this one is an example of an instance wherein the proposed or the possible primary key is too long and the semantic meaning is not that clear. So we make use of surrogate primary key. So in this case, instead of using the combination of date, time, start, time, and room, you can just create a surrogate primary key. Let's say 1, 2, 3, 4, among others. Now let's take a look at some design cases. If we would like to implement a one-to-one relationship, the foreign keys work with primary keys to properly implement relationships in relational model. We usually place the primary key of the parent entity on the dependent entity as the foreign key. Now, if you have a one-to-one relationship, you have two options for selecting and placing the foreign key. First, you can place a foreign key in both entities, or you can place a foreign key in just one of the entities. Okay, the following table summarizes the different implementations of the one-to-one relationships in the selection of a foreign key. For the type 1, we have one side that is mandatory and the other side that is optional. What we would do is to place the primary key of the entity on the mandatory side in the entity on the optional side as a foreign key and make the foreign key mandatory. For type 2, if both sides are optional, you can select the foreign key that causes the fewest nulls, or you can place the foreign key in the entity in which the relationship or role is played. And lastly, for type 3, if both sides are mandatory, you can take a look at the case 2 or consider revising your model to ensure that the two entities do not belong together in a single entity. Because most of the time, if you have two entities that have a one-to-one relationship and is both mandatory, then maybe they are better off in just one entity. Here we have an example of a one-to-one relationship wherein one side is mandatory and the other side is optional. And as you can see, what we have done here, we took the primary key of the mandatory side and placed it as a foreign key in the optional side, which is the department. Design case number 2, maintaining history of time variant data. Now, what do we mean by time variant data? Time variant data are data whose values change over time and for which a history of the data changes must be retained. This one requires creating a new entity that has a one-to-many relationship with the original entity, and the new entity contains the new value, the date of the change, and other pertinent attribute that might be useful for you to still store. Usually, we are using the time variant data when you would like to capture the changes, for example, in the salary of your employees or in their position as they go along the journey in your company. Here we have an example of maintaining history of time variant data, wherein the employee table has our current data and we have created a new entity to capture the historic data. In this case, the historic data refers to the salary history of the employee. If you would like to extend the previous example to also capture the history of the managers, of the employees, and the departments, you can do that by adding a manager history entity and capturing their primary keys as a foreign key in the manager history. And as a final example, we are creating a new entry, job history, that captures the history of the job or the position of an employee within the department and within the company. Design case number 3, fan traps. Design trap occurs when a relationship is improperly or incompletely identified. It is represented in a way not consistent with the real world. Now, we have a fan trap if one entity is in two one-to-many relationships to other entities. This one produces an association among other entities that are not expressed in the model. And usually, fan traps are commonly committed by starting database professionals. Let's take a look at an example. So here we have an incorrectly designed entity relationship diagram with a fan trap problem. As you can see, the division has a one-to-many relationship with the players, and the division also has a one-to-many relationship with the team. So we can see here one entity that has a one-to-many relationship with two independent entities. But it makes sense if you think about it. However, this is a fan trap because, as we have said, a fan trap occurs when you have an entity that has a one-to-many relationship with other entities. The correct way to express this is by following the next slide. So instead of expressing division having a one-to-many relationship with the players, it makes sense that the division only has a one-to-many relationship with the team, and the team is the one that has a one-to-many relationship with the players. Design case number 4, redundant relationships. This one occurs when there are multiple relationship paths between related entities. This must remain consistent across the model, and it helps simplify our design. Here we have an example of a redundant relationship wherein we can see that the division to the player has two paths. So from the division, we have a path directly to the player, which is a one-to-many relationship, and we also have a path going through the team. As you can see, the path from division to player is a redundant relationship, so we can just get rid of that. So in summary, the extended entity relationship model adds semantics to the entity relationship model via entity supertypes, subtypes, and clusters. A specialization hierarchy depicts the arrangement and relationships between entity supertypes and entity subtypes. An entity cluster is a virtual entity type used to represent multiple entities and relationships in the ERD. Natural keys are identifiers that exist in the real world, and composite keys are useful to represent many-to-many relationships and weak, strong identifying entities. Also, surrogate primary keys are useful when there is no natural key that makes a suitable primary key, when the primary key is a composite primary key with multiple data types, or when the primary key is too long to be usable. Time-variant data refers to data whose values change over time and require that you keep a history of data changes. And lastly, a fan trap occurs when you have one entity in two one-to-many relationships to other entities, and there is an association among the other entities not expressed in the model.